So next we can discuss ICT and constants of motion. Here we have to discuss two different cases. First, the translation of a system from one point to another in phase space, and the second one is the rotation of the system. So first we can consider the translation of a system. So during translation there is only change in the coordinate of the system. Now let us assume that there is only an infinitesimal change in the coordinate of the system, and let it be equal to epsilon. We know that delta Q is equal to epsilon into dou G by dou Pi. In the last class we have seen this equation, that is the infinitesimal change in the coordinate delta Q is equal to epsilon times dou G by dou Pi, where G is the generating function for infinitesimal canonical transformation. Now we assume that this delta Q is equal to epsilon itself. Epsilon is a small positive value. Suppose the system is displaced from one place to another, or it is translated, or it undergoes translation by a very small amount epsilon, then this epsilon is equal to epsilon into dou G by dou Pi, or dou G by dou Pi is equal to 1, or dou G is equal to dou Pi, or the generating function G is equal to, we may write this as equal to sigma I Pi, or integration or integral dou Pi, or it is equivalent to Pi. So the generating function is the total linear momentum. Total linear momentum is the generating function here. So in the case of ICT and translation, the generating function is equivalent to the total linear momentum of the system. And also, if H is the Hamiltonian of the system, since there is only a very small change in the coordinate delta Q of the system, the variation in delta H will be equal to 0. And we know that delta H is equal to epsilon times the Poisson bracket of H with G, where G is the generating function. Now in this case, this is equal to epsilon into H. G is the total linear momentum. And since delta H is equal to 0 for this translation, epsilon is a positive quantity and it is not equal to 0. So we may write H sigma I Pi is equal to 0. H sigma I Pi is equal to 0. That means if H Poisson bracket of H with another function is equal to 0, then this function is a constant of motion. That is, here sigma I Pi is constant, or sigma I Pi is conserved. So for translation under ICT, the generating function is the total linear momentum, and the total linear momentum is conserved, or it is a constant of motion. So next we can consider the case of rotation. Second case is rotation of a system about a preferred axis, and here we take Z as the rotation axis. So the system is rotating about the Z axis in the anti-clockwise direction by a very small amount d theta. This is the angle through which the system is rotated. Now we may take the coordinates x and y as the Cartesian coordinates as the generalized coordinates, so that x, y, z are the coordinates, and we are rotating the system about the z axis, so there won't be any change in the z value, but there will be change in the x prime and x and y values. And we may write the values as x prime, y prime, and we may represent this in terms of rotation matrix. So the new coordinate after rotation will be equal to x prime, y prime is equal to matrix cos theta minus sin theta sin theta cos theta into x, y. So x prime, y prime are the new coordinates after rotation, and we know that when theta is very small, cos theta is approximately equal to 1 and sin theta is approximately equal to theta. Here theta is d theta. So we may rewrite this as equal to cos theta is 1 minus d theta. Here sin theta is d theta and cos theta is again 1 into xy. So new coordinates x prime, y prime is equal to this much. We may expand this so that x prime is equal to x minus y into d theta, and y prime will be equal to x d theta plus y, x d theta plus y and x minus y d theta. Or we may write delta x as equal to, delta x is x prime minus x. So that will be equal to minus y times d theta, and delta y will be equal to y prime minus y is equal to x into d theta. So these are the values that we get after rotation through a very small angle d theta about the z axis, and so naturally delta z will be equal to 0. There won't be any change in the z coordinates of the system. Now we may write the changes in the momentum coordinate pix as equal to minus piy into d theta. Then piy is equal to pix into d theta. Similar to this, we have written the delta value, here delta pix and delta piy. Delta pix is equal to minus piy into d theta, and delta piy is equal to pix into d theta. These are the changes in the momentum coordinate. Now from the general expression, again we can write delta qi. We have seen that the expression for delta qi is epsilon into dou g by dou pi, and delta pi is equal to minus epsilon into dou g by dou qi. These are the general expressions. Now using these equations, we may take qi, or we may substitute qi as x and pi as pix. So and epsilon is equal to d theta in our special case. Now these equations becomes delta qi instead of delta qi, delta x. Delta x is equal to d theta into dou g by dou pix, and instead of delta pi, delta pix is equal to minus d theta into dou g by dou qi. So dou g by dou x. These are the next set of equations. Now we may compare these two equations. The first we have written delta x is equal to minus y into d theta, and here delta x is equal to d theta into dou g by dou px. So we can compare this term and this equation and this one. So right hand side is same, or d theta is equal to dou g by dou pix. d theta into dou g by dou pix is equal to minus y into d theta. So d theta and d theta gets cancelled. So dou g by dou pix is equal to minus y, or dou G is equal to minus y into dou Pix. And from this, G can be written as minus y into Pix. So, the generating function G is equal to minus y into Pix. Now next we can consider this equation delta Pix and this one, that is delta, the expression for delta Pix. So the right hand sides are minus d theta into dou G by dou x is equal to minus Piy into d theta. Here also d theta gets cancelled, minus gets cancelled. So dou G is equal to Piy into dx. Dou x. Piy into dou x, or G is equal to Piy into x, or xpi. G is equal to xpi. So we can compare these two or combine these two values so that the combined G value or generating function can be written as x Piy minus y Pix. So this is the combined generating function for rotation. G is equal to x Piy minus y times Pix. Now this is the z component of angular momentum. Angular momentum L is equal to r cross p. L is equal to r cross p. It is equivalent to this z component of angular momentum. We can prove that, or I will show you, because r cross p is L is equal to r cross p, that is equal to I j k x y z p I x p I y p I z are the components of momentum. Then this will be equal to I into y into p I z minus z into p I y minus j into x p I z minus z p I x plus k into x p I y minus y p I x. So this is the z component. This is L. So this one is the z component of angular momentum. L is equal to Lxi plus Lyj plus Lzk. So Lz is equal to x Piy minus ypix. So this is the generating function that we have obtained. So for rotation about the z axis in the anti-clockwise direction, the generating function is the z component of the angular momentum. So in this case also, since the rotation is very small, this will leave the Hamiltonian unchanged, or the change in Hamiltonian delta H will be equal to epsilon times H, and G, instead of G we may write Lz, and since it leaves the Hamiltonian unchanged, this value will be equal to 0. Here epsilon is equal to d theta. Since d theta is non-zero, we may write H Lz is equal to 0, or Lz is a constant, or angular momentum, z component of the angular momentum is the generator of rotation about the about the z axis, and also the angular momentum, z component of the angular momentum remains constant. So these are the two conclusions that we obtain from this.